Hello, everyone. So this talk for today is reserved for the gold partners of this year's conference, Yandex, who have significantly contributed to achieving everything we envisioned. This is another milestone in our long-standing collaboration, and we hope there will be many more. Now we have Vladimir Platonov, TTS department lead at Yandex. He will be presenting Building Next-Gen Speech Synthesis for Bookmate audiobook service. In this session, he will share the journey of developing advanced text-to-speech technology for audiobook production. Vladimir will discuss their baseline systems built with just 90 hours of training data and its deployment across more than 100,000 books. He will also delve into the advancements of next-generation TTS, leveraging extensive datasets and neural architectures, and how user feedback and crowdsourcing ensures quality. I would also like to ask the audience, it is suggested that you come forward because there will be certain graphs that you will be able to see better if you're closer. So, give a warm welcome to Vladimir.
Hello everyone, nice to see you. I'm Vladimir Platonov, text-to-speech department lead at Yandex. And today I will tell you a bit about building text-to-speech for online audiobooks service. So, let me tell you a bit about my department. We are around 30 people, and we have three main products. The first one is a voice assistant living in our smart devices with almost 90% of market share. You may also know her is Yasmina in many countries. The second one is a voice-to-voice video translation at Yandex browser. We could take a video at one of the main European or Asian language and translate, adapt it at Russian, English or Kazakh languages. And the third one is a Yandex Books, which we will talk about today. Also, we have fundamental research to push our technological boundaries forward. Okay, let me tell you a bit about Yandex Books. It's one of the biggest Russian audiobooks service. It has in a library about 250,000 books, but sad fact, only 10 to 15% of them will have audio version in near time, because it's a long process and it's also very costly. Another interesting fact that with our default text-to-speech synthesis at Yandex browser, our users in previous years listened to almost 4 million hours. That's about, I don't know, maybe 500,000 books a year. That's quite a lot. So, what would we discuss today? First of all, we will talk about what a user wants from audiobook and how to build a base model. After that, we will talk about enhancement of a base model, and then we will talk about next generation synthesis, and of course, question and answer section. So, let us begin. What a user wants. From academic studies and our research, we found out that the user prefer calm, soft, enveloping voice. It may differ, preference may differ based on genre of a book, but that thing stays in common. The next one is a non-monotonic speech, because if I would tell you in this robotic voice, your attention will go out in no time. Next, the hierarchy of pauses. Pauses is an important aspect of intonation. We could use it to accent something or to divide the sentence in some semantic segments for better understanding. Next one is my favorite metric. It calls don't get tired from synthesis. For example, I took your favorite book, I synthesized 5 minutes of it and give you to listen it. And I ask you only one question. Would you like to continue? Because you know, you could always synthesize a short sentence that sounds perfect, but in the long run, the problems are gonna show up. Close to non-monotonic speech is a diverse of intonation. For example, even a simple sentence could be said with different accents on a different part of a sentence. And of course, in a fiction book, you have to use emotions to be happy or angry or sad or something like that. And the last one, but not the least, is non-speech sounds like laugh or breath or something like that. So, how to choose your voice actor? We build a pool of candidates, around 50 persons. Most of them are voice actors, either amateur or professional, and others are aspiring actors with education. And we made them to read a few dozen lines from one of the literature books called Dr. Zhivago. And sadly, only few of them could read it without losing quality towards the end. Some of it starts to breathe, some of them starts to be monotonic or something like that. And another sad fact that the best voice actors want more money than whole our research group. We can afford it, yeah. And after internal voting, we came with 2 candidates and we decided to record them both for the 30 hours of speech. We prepare a diverse set of texts. The main rule here is the text should be the same that you would use your model on. Like, if you have different lengths, you should put different lengths of sentences into train set. You should also put exclamations, questions, every specific things that you have in your language. And also, you have to use every pair of fonts in your language. So, do it and train the base model.
Which would permit it to provide adequate protective manpower for all situations.
That's our speaker David in English. Okay, so now we have calm, soft, enveloping voice, and we have a non-monotonic speech because we read different intonations from our speaker. Let's talk about enhancement of a base model. First, hierarchy of pauses. As I said before, the pauses are a very important aspect of intonation. For example, it allows us to divide a long sentence into shorter ones to help us better understand the idea. Okay, let's talk a bit about our base model. First one, we have a text. Next, we do some pre-processing. Pre-processing is a process of removing the numbers or abbreviations and put it in a just simple text. And also, after that, we turn this text to fonts. Fonts is how we spoke it, not how we write it. The fonts goes to acoustic model. Acoustic model is a deep learning model which turns fonts into MEL spectrogram. MEL spectrogram is essentially a picture. On x-axis is a time, on y-axis it's a frequency, and the xy point is an energy on that frequency at that time. And finally, we have a vocoder. Vocoder is a neural net that turns a MEL spectrogram to a WAV file. It's pretty much a soft task, and we will not talk about it much. So, let's talk a bit more about our acoustic model. We use a model based on Tacatron 2. It's a Google article from 2018. It has an encoder and after-regressive decoder, which predicts the MEL spectrogram step by step. And another important thing here is a local sensitive attention. It helps us to build an alignment between phones and times. Take a special look at the attention, because the yellow one part is phones and when it spoke, and the spaces between them, it's a pauses. We could run this decoder from all our train set and find all pauses. And we cluster them into several bins based on their length, like a small one will be the first bin, the big bit second one, and so on. And we create new pause tokens from SIL1 to SIL5. Usually 1 means it's 2 MEL frames, and 5 means it's 32 and more MEL frames. And now we can improve our control over speech, and we could also predict these tokens from the text. So we could use it on every text that we haven't seen before. Okay, so now we have hierarchy of pauses. Okay, but what about connecting different sentences? For example, I could say, okay, I got this, thank you. But we would like to hear something like, okay, I got this, thank you. You see how the pitch goes. So Of course, we could just put whole the text into our model, but since it's autoregressive and just predicts one mil frame, it's pretty long. And also on the long sentences, this model goes brrr sometimes, and that's not nice, believe me. So what's our answer? It's an article from Google. It's called PNG BERT. It's essentially a simple BERT model which took two sequences, the graphemes and the phonemes. We mask the phones and we try to predict it from the context. But what's important here? Yes, it helps to the current sentence, but we could also add a left context of our text. So we could add this context to our current sentences. And this use only one BERT model, and that's cheap one things. So what the PNG BERT does? First of all, it helps fix pronunciations in the difficult cases, because the pre-trained model saw, I don't know, millions of texts, maybe dozens of millions, while our base model saw only, I don't know, dozens of thousands. It also helps to connect the consecutive sentences without resynthesizing, so we have the speech contour goes on. On a side-by-side metric, we have a win 55 to 45. That means that every 10th example is better. So now we could also don't get tired from the synthesis. Let us check.
The old woman was a witch shadow, hair like matted spider webs, hooded round darkness of features, eyes like glittering jewels. Is he not small for his age, Jessica? The old woman asked.
You may view the book, I guess. It's a Dune. I believe it was okay, but the dialogue part was a bit out because we would like to hear a different voice. So let's go to our next generation synthesis. A few years ago, we have a funny experiment. We ran side by side from ground truth against synthesis on short sentences, and synthesis won. And that's funny because, well, we all knew that syntheses are not that good yet. So why? Because humans are non-ideal. If you took my presentation, I breathe through, mostly because I'm nervous. I stutter, I say or I speed up when I say something boring, and I have an emotions when I don't know, maybe I'm happy when I talk about my favorite part. So, what is the answer? First, let us remember what's interesting happens in a deep learning field. In NLP, we have GPT-like model. In a CV, we have a diffusion models. And if we put them together and get a single motivated engineer with a spare time, we could create a tortoise dataset by James Bedker. That's really interesting because he didn't make an article or something, he just created this model in a separate time. So, how do we use a GPT model in speech? Because speech is continuous with floating embeddings. Another Google article, as you may guess. We use a technique called vector quantization to turn audio to a number of discrete tokens. So essentially now my speech is, I don't know, 13, 55, 182, and so on, and so on, and so on. It's essentially built from autoencoder. On the center you see some code book with discrete tokens. We just update them as a cluster sizes. So let us discuss our next gen in details. First of all, what we have on input? We have a text and some what called audio prompt. The text is what to speak, the audio prompt is how to speak. So we're essentially trying to copy intonation and the voice from this prompt. Okay, so now we have text tokens, audio tokens from prompt, and we could predict discrete tokens of output with GPT-like model. So essentially we took the discrete tokens and predict discrete tokens. After that, we took the latents, it's next to final layer, and do essentially a text to image. We predict from those latents the mel spec as a picture with diffusion process. And after that, we invert mel spectrogram to WAV with vocoder. As I said before, there's nothing fancy here. Also, there is one funny moment. GPT are sometimes not that good because the sequence they're generating could be pretty bad, like they lose a word or they goes with a strange intonation. So we use additional network with contrastive learning for scoring hypotheses. The GPT generate 32 hypotheses and we score them with additional model to take the best one. So another interesting point that almost all current generation article and SOTA article, it's somehow a tortoise which is not an article. They just maybe fix a few things in them. So our roadmap for tortoise. First, integrate our means of control. Second one, speed up the model because it's almost 2 magnitude bigger. And 3, increase the quality of our synthesis. Okay, so what's the universal SOTA solution? Take the best open source you have, speed up training at least a magnitude so you could experiment a lot, fix bugs and train test misalignment, and add your features. Here you could see pictures of my colleague who used this technique several times at different competitions and won. Okay, so let's talk a bit about speeding up the training. We have 3 main building blocks in our model. First, the text padded by end of sentence tokens. The second one, the MEL spectrogram padded by silence. And the third one is discrete audio tokens and latents. But we couldn't really pad them because if you put a sequence in GPT with a lot of silence in end, it won't know when to stop while training. So, how does the baseline diffusion training looks in Tortoise? We padded all MELs to 12 seconds with silence, so now we predict only 12 seconds MELs. We calculate discrete tokens of fixed length from these MELs. We calculate latents of fixed lengths, and we diffusion translate latents to the MELs. So now we fixed every length, and we could train. But this thing is really slow, because it took us almost 30 days to train a first one on a 8A100. That's quite a lot. So the pros are it works. The cons, we have either train test misalignment or we will always predict at 12 seconds, and that's a deal breaker. We either station heavy latent data or calculating it online. And for one batch gradient accumulation, we have to do 16 forward backwards. That's a death, actually. So what's our answer? First of all, we add mask to all layers. Now we don't need to predict 12 seconds, we could predict every length. We also increase mean batch size. Bigger batch size means bigger learning rate, and that's good for our model. Also now latents weight as much as audio, it's just x2 at space, so we could store them somewhere away. Also add dynamic batching by audio length, so you put in one batch audios of pretty much same length, less masked areas, more tokens on batch, more learning rate, and so on. Also, of course, add mixed precision, minus 40% training time. Add efficient CUDA calls, minus 30% of memory allocations. And totally, we go from 30 days to 3 days, and now we could experiment a lot with our cards. Also, another hint, add touch compile only at the end because it have heavy restrictions on code of your model. So let's listen a bit more.
The old woman was a witch shadow, hair like matted spider webs, hooded round darkness of features, eyes like glittering jewels. Is he not small for his age, Jessica? The old woman asked.
As you can hear, the synthesis gets really better. We use 5 aspects side by side to compare this to the previous one. We have such aspects as sound quality, naturalness, speed, intonation, and overall impression. And overall impression won 64 to 36, and on dialogue basket it won almost 78 to 22, and that's a lot, believe me. So, what's the results? The arXiv articles are useful, like with PNGBird. The GitHub repo with a lot of starts too, like Tortoise TTS. Start with something good and only after that go with something genius. And we are here, but we have a lot to go. Thank you for your time. I'm ready to answer all your questions.
Hello.
Are there any questions?
Yes. Yes. Hello. Thank you for your speech. And I just want to ask you about the next. You hear me?
Yeah.
Like this. Okay, now you hear me. Thank you for your speech again. And do you have the next step of this text-to-speech to get the roles of the person inside the books? And another one, and is the next question about this again, the role and the character of the person.
Okay, so my idea is that we have to use what's called text prompting, like in text to image. So you could use GPT to process the book and give to all sentence something like text prompt, like here Alice says with this voice, and he says with this emotion, and so on. And we train the TTS to learn with these text prompts, so it could listen to them and generate the book with all our hints. I believe something like that.
Cool, thanks.
Any other questions? So, of course, you may ask the speaker after he finishes.
Okay, thank you.